Presenting Team 25053, the exploration of thermal diode effects of nitinol-based shape memory alloys. Does this often happen to you? Does your computer keep overheating? Maybe your phone. Or maybe your personal missile keeps failing to deliver its payload of friendship and kindness before the electronics inside are fried. That's where Team 25053 comes in. Our project is all about thermal management. We've experimentally demonstrated that nitinol functions as a thermal diode by designing a test setup and collecting data. This unique material helps regulate heat flow in and out of sensitive electronics, making it useful in everything like everyday electronics like phones or laptops. Our project focuses on using nitinol's ability to absorb energy in the form of heat to our advantage to get heat away from sensitive electronics inside a missile. So class, nitinol is a very unique alloy in the sense that you can plastically deform it into any shape you want. When you reintroduce energy into the system, in this case it would be heat, you can reorient its atomic structure into its initial form. Here you can see the nitinol is drawn out into a wire shape. I am now plastically deforming it so it has a bit of a different structure than before. There are two main types of nitinol, shape memory alloy and superelastic. Superelastic only occurs below room temperature, constantly absorbing energy, continuously reforming itself, and remembering its original shape. For our project, we are going to be using nitinol's ability to absorb heat during its phase transformation. We are going to assess the feasibility of a nickel titanium thermal diode by using this small sample. Introducing Nicholas Deanda, who did our modeling, Michael Paff, our procurement lead, Ileana Carpio, our integration lead, Adam Bejarano, our research lead, Tara Brady, our documentation lead, and Ranger Stevenson, our team lead.
This project started because we were working on smart alloys like nickel titanium for use as energy absorbers for civil engineering structures and other applications. Yeah, since they are so good at absorbing temperature or releasing latent heat, we thought that we might use them as part of a thermal diode.
We initially used X-ray diffraction to verify the composition of our nitinol sample, but the results were inconclusive. A couple months later, we discovered that this was due to nitinol being naturally radiopaque, meaning X-rays passed through it directly with minimal interaction. This property explains why in medical applications nitinol is often paired with platinum or palladium to help with medical device imaging. To quickly verify that our sample was indeed nitinol, we plastically deformed it with a noticeable bend and then placed it in boiling water. The sample returned to its original shape, confirming the shape memory effect characteristic of nitinol. Since X-ray diffraction gave us inconclusive data and the thermal bend test cannot precisely determine the composition of nitinol, we use energy dispersive spectroscopy, or EDS, as an alternative method to analyze the material's composition. EDS uses a high-energy electron beam to excite atoms, causing them to emit characteristic X-rays that correlate to specific elements. By doing energy dispersive spectroscopy on the scanning electron microscope, we were able to collect conclusive data of the exact composition of our nitinol samples. To build our test rig, we started with insulated fire brick. We cut it down to the correct size, sanded it for a precise fit, and used insulating mortar to bond the bricks together. Once that structure was complete, we set it into an aluminum frame. For the samples, we had to drill holes to an exact depth to place the thermocouples, which would collect temperature data during the testing. After assembling everything, we ran a rough test and immediately realized our initial design had some serious flaws. Accurate and precise data collection is the core of our project, but we ran into a problem. How do we run the wires from the inside of the test rig to the outside without compromising the setup? Our first idea was to drill straight through the rig, but that made it nearly impossible to swap out the samples. So we pivoted. Instead, we designed modular panels that attach directly to the samples themselves. This way, we can swap out the samples, panels, and lid all in one go, making the whole process cleaner and more efficient. Here, we have our setup to determine the feasibility of a nickel titanium thermal diode. It consists of two DC generators which supply power to our test rig. Inside of our test rig, which is made of insulated fire brick and aluminum housing, inside we have the nickel titanium sample as well as the aluminum. We have the panels and the lid, which allows for easy swapping to increase the amount of tests we can run within a given amount of time. These thermocouples are hooked up to our data logger. Our data logger is then hooked up to the data collection software, where we are able to monitor the temperature in real time. During the phase transformation, the thermal conductivity decreases as heat energy is absorbed to reorder nitinol's atomic structure. This resistance graph represents the nitinol aluminum thermal diode. The heat flux can then be modeled in two directions, in the forward bias from the aluminum to nitinol and in the reverse bias from nitinol to aluminum. The rectification ratio can be calculated by dividing the forward bias by the reverse bias. This transport-based theory proposed by Dr. George Francis Conus is significant because our primary objective is to calculate the rectification ratio and determine whether nitinol is a viable material for real-world applications based upon its ability to push heat out of the system while not allowing it in. The goal of our project is to evaluate the feasibility of using nitinol as a thermal diode, something that allows heat to flow preferentially in one direction. We collect temperature over time data and used it to generate three key graphs: thermal time difference, heat flux, and rectification ratio. Early on, our data was inconsistent. We discovered there was an issue with uneven heating. Our patch heaters didn't match the assumptions in our models. To fix this, we redesigned the thermocouple placements to ensure one-dimensional heat flow through the sample. That change gave us cleaner, more reliable data. Thermal time difference graphs shows us how long it takes the nitinol and aluminum to reach 100 degrees Celsius, a critical failure point for electronics. The more nitinol delays heat, the better it performs as a thermal diode. Heat flux graphs capture energy transfer in both the forward and reverse bias. In the forward bias, heat moves from the aluminum side into the nitinol. In the reverse bias, heat moves from the nitinol side into the aluminum. This lets us compare directional heat flow behavior. Finally, the rectification ratio graphs use the forward and reverse heat flux. Aluminum is shown at a constant 1, meaning there is no directional preference for heat flow. But with the nitinol, we see a spike near its phase transformation temperature. That spike is key. It means nitinol resists heat more effectively in one direction, indicating a successful thermal diode effect. In all, Team 25053 has met our sponsors' goals and requirements, and we are proud to say that we have successfully achieved the project goal we set out to accomplish this year. Thank you to our sponsor, Dave Staggers and Raytheon, our mentor, Jeff Wolski, and the University of Arizona for making all of this possible. Thank you.